All right. In section 4.8, we're going to be looking at antiderivatives, but like I said, you guys have already done these. Just don't be afraid of them. We're just putting a name to what we've already done. All right? So a function capital F is said to be an antiderivative of a lowercase f on an interval I if the derivative of the antiderivative is the function. The derivative of the antiderivative is the function. That's probably the most complicated thing here, and that's what this notation means. The derivative of the antiderivative is the function. So looking at this, if f of x equals 1 over x, find an antiderivative for each of the functions. What function can we take the derivative of and get 1 over x? ln x, right? But we've also got a constant c here. What about g of x? Well, isn't that going to be 8 ln x plus c? See how that works? If you got a constant on top, you just got that constant multiple out in front. But isn't this equivalent to the natural log of x to the 8th? Using the power rule, oops, plus c. How about h of x? What can I take the derivative of and get 4? Minus, look at the pattern we just did. This is going to be the natural log of x to the 5th plus c. So where c is any constant.
Why do we have to put the c? Yeah. So do we have to put c since c?
Oh look, theorem 8. You have to put the plus c.
Okay.
Here's a table of common antiderivatives. The most important one, I think, is this one right here. It's the new power rule. The trig functions will happen. They'll occur. Remember when we took the derivative with respect to x of x to the n? What we said was we add, bring the n down, subtract 1 from the exponent, right? Well, guess what? It's no big wonder that the antiderivative is going to add 1 to the exponent instead of subtracting. We divide by the new exponent instead of multiplying by the old. We're just undoing what we did to get to the derivative. Okay? So instead of subtracting 1, we add 1. Instead of multiplying by the old, we divide by the new. Okay? That's your power rule. So let's use the power rule then and find an antiderivative for each one of these functions. Alright? So we have capital G of x. Add 1 to the exponent. And what do you get? So we have a negative 3, x to the negative 3, and then divide this by the new exponent of negative 3, and we get g of x equals x to the negative 3 plus c. Well, gee, you can check your antiderivative by doing what? Take the derivative and see if you get back what you started with. All right, h. It's doing right. I guess it matters. Add 1 to the exponent. What do you get? Negative 3. Divide by the new exponent and put plus c. You could write this as negative 1/3 x to the negative 3 plus c. Okay. Add 1 to the exponent. divide by the new exponent, add 1 to this exponent, what do you get? Divide by the new exponent, plus 4x plus c. So we would clean this up and just write negative 1/3 x to the negative 3 plus x squared plus 4x plus c. It's stuff you've already done. Here's the constant multiple rule, the negative rule, sum or difference. Basically, it's still everything that we could do before, we can still do. Okay? Example 3. A. I will do it like this. If f of x is equal to x to the 5th, let's find the general antiderivative. Cap f of x is equal to what? Add 1 to the exponent and divide by the new exponent and add c. B. You may want to rewrite this just like we did before. We have g of x is equal to x to the negative 1/2. Finding the antiderivative. Add 1 to the new exponent. What do you get? X to the 1/2. Divide by the new exponent. But dividing by 1/2 is the same thing as multiplying by 2. And don't forget your plus c. C, we have h of x. The antiderivative. If we have a constant here in our angle, this goes back to the constant multiple rule, or actually it's on our shortcuts. We have 1 over k sine kx would be the antiderivative. I'm sorry, negative 1 over k. All right. What could I take the derivative of and get sine? Negative cosine. So there's where I put the negative cosine. The angle has to be the same, so that's going to be 2x. But I don't want a 2 there, so I need to put a 1/2 for my chain rule and then put plus c. Do you see how you just kind of undo the derivative in your mind? You're just working backwards, which is very difficult if you don't have the forward part worked out. So if you don't have these derivative rules memorized, the antiderivatives are going to be darn near impossible, which is why I've kept stressing you need to memorize these rules for derivatives. If you were to take the derivative of this, you'd have to use the chain rule, which means you'd multiply by 2, so we got to counteract that multiplying by 2 by dividing by 2. All right, D. We have the antiderivative of cosine, is going to be positive sine x over 2. And to counteract the multiplying by 1/2, I've got to multiply by 2. So this is 2 sine x over 2. E. Antiderivatives for exponentials are just as easy as the derivatives are. You just got to remember to divide by that constant there. So it's going to be negative 1/3 e to the negative 3x. I forgot my plus c last time. Sorry. Take a point away from me. All right. Why do I have to put the minus 1/3? Because the derivative of negative 3x is negative 3, and you want to counteract that negative 3. So, and then F. We got to, normally when we take the derivative of 2 to the x, we get a ln 2. Well, we've got to undo that ln 2. So we're dividing by the when you take the derivative of 2 to the x, you get 2 to the x, your exponential, times the natural log of the base, which is 2. Well, to undo multiplying by the ln2, we have to now divide by the ln of 2. It's one of those obscure rules we don't use very often, and I don't think I've ever put it on a test, but it's there. Okay. Now, the collection of all antiderivatives is called the indefinite integral. This is the symbol that we use for an indefinite integral, which just means find the antiderivative. We're just introducing another symbol now. So, find the most general antiderivative or indefinite integral. Check your answers by differentiating. Let's rewrite this as the integral of 9y squared minus 5y to the negative 3/7 dy. This just tells you the variable you're finding the antiderivative with respect to, and in this case is going to be y. So this is going to be, what do we do to the exponent here? Add 1 and then divide by the new exponent. Minus, if we add 1 to 3/7, we get 5y to the 4/7 divided by 4/7 plus c. Now we want to clean this up. So that's going to be 3y cubed minus 35/4 y to the 4/7 plus c. Can we check and make sure we did this right, or are we just going to trust that we did this right? Fine, but we did it right. All right, number 5, example 5. Find the most general antiderivative of the indefinite integral. It might help, once again, if you rewrite this. We can rewrite this as the integral of 4t cubed plus 1/3 t dt. So when we find the antiderivative, what do we do to the exponent? Add 1. So this is going to be 4t to the 4th, and then divide by the new exponent, plus 1/3 t to the 2nd, and divide by the new exponent. So this, when we clean it up, is going to be t to the 4th plus 1/6 t squared plus c. Or you can put t squared over 6. It does not matter. Okay. All right. In example 6, I'm just wanting you to find the derivative, or an antiderivative, for each one of these when c is 0. So now I'm telling you the value of c. Okay? We could rewrite this as 3 times the integral of 1 over the square root of 1 minus x squared dx. Well, when we find the antiderivative of this, that's our inverse sine function. Yeah, you got to know the derivative of your inverse trig functions if you're going to recognize the antiderivative. This, another way to write it, is 1/6 the integral of 1 over x squared plus 1. And which trig function is this? Tan inverse. And c is 0, we're told. This one I could rewrite as green. The antiderivative of 1 over 1 plus 6x squared dx.
What? 6x? Oh, I got you.
Look at the parentheses. This happens to be, and you may not recognize it right away, it's 1/6 tan inverse 6x, because you've got a differential here that you have to worry about. The chain rule when you take the derivative is the 6. So to counteract that, we get the 1/6. Okay? And then the last example is one that's been a fair game, and it's a fair game on this test. Find the function y satisfying the second derivative acceleration. Second derivative's acceleration, right? When the initial velocity is 4 and the initial height is 8. This is one that we've been doing if we do position, velocity, and acceleration. All right, so here's the second derivative. The first derivative is going to be equal to the antiderivative of the second derivative, 6 minus 30x. So that means that the first derivative is equal to 6x, not minus, plus, minus 15x squared plus c. But now we use this. If x is equal to 0, that derivative is equal to 4. So the derivative is equal to 4 when x is equal to 0. So guess what's equal to 4? C. So now we have the second derivative is 6x minus 15x squared plus 4. No, this is the first derivative.
You said it backwards.
Oh, I'm sorry. Sorry. Now the position is equal to the antiderivative of the derivative, which is 6x minus 15x squared plus 4. So that means that the antiderivative is 3x squared minus 5x cubed plus 4x plus c. But look at this. What is c equal to? When x is equal to 0, c is equal to 8. So then our final answer is y is equal to 3x squared minus 5x cubed plus 4x plus 8. And we're done.